Okay. So by the way, in the 15th of April, so next class, we will have quiz one. Okay. So that is open book quiz. Okay. So you can bring paper materials, but you are not allowed to bring any electrical device. Okay. But you can print out every materials that we study during this course. Okay. And yeah. And assignment one that is announced already. Okay. So please, yeah, do that. Okay, by the deadline. Okay. And also quiz one, I mean, material, I mean, I will contain the quiz content from lecture one to lecture six. Okay. So, I mean, by the transformer, okay, this lecture, the quiz one will cover. Okay. Okay. So last time we learned about the transformer. Okay, in general transformer we have learned. Okay, but from now on we will see how these transformers can be applied to the vision domain. Okay, so this VIT is the abbreviation for vision transformer. Okay, uh, proposed in ICLR 2021. Okay. And so far, we learned the transformer, how to say, their input to this transformer was the word sequence, okay, which means one-dimensional vector. Okay, their one-dimensional vectors, their sequence was the input to the transformer. But now we have to input the images, okay? Rather than the sentence, we have to process these images, okay? And the simplest way to, input these images into the transformer might be dividing the images into subregions, okay? And then then flattening each pixel values. For example, if this patch is 28 by 28, then we will make them as this dimensional, one-dimensional vector, okay? By flattening 2D patches, we can make it into vector and then supplement that as the input to the transformer, okay? That's how this Vision transformer, they are inputting the images into the transformer. Okay. And another thing you have to remember is this token. Okay, we call the input to the transformer as the token. Okay, and we need the Vision transformer that's proposed for the classification task, image classification task. So this image classification, we will classify images according to the main object, their classes, okay? So classification, our output have to have some, the semantic classes, their probability vector, we have to output, okay? And in the transformer, another thing you have to remember is in the Vision transformer, we will use only the encoder. Okay, so originally in the transformer, there are encoder-decoder architecture, right? But we will only use encoder structure for Vision transformer. And you may already remember that encoder, they are involving only the self-attention mechanism, not having cross-attention mechanism, okay? Cross-attention was only in the decoder. So in the transformer encoder, as you see, uh, I mean, because the input is now becoming the images rather than the sentence, we will divide images into subregions like this and flattening each subregion patches and then input it, okay, to the transformer as if we did for the sentence input. We input this image, flattened image patch values, and then we will apply the self-attention mechanism by converting each image into key query values, right? And then further apply some MLP and iterate this for L times. That's the transformers encoder, okay? And previous original transformers, we use this as the decoding the features for the decoder, but we will not involve that in the Vision transformer, but instead we'll further map this part directly map these final inputs of the encoder to the class probability, okay? Because there is no decoder now. We are involving only the encoder. So we will further map some of the transformer encoder's output directly to the class probability, okay? So Vision transformer, its architecture is quite simple, okay? Are you guys following this? Okay. And also, the other thing you have to notice is originally, transformers encoder are outputting same dimensional, same number of output as the input number, okay? So when we input, 100 tokens to the transformers encoder, then we will output 100 output tokens, okay? But there's no arrows in this output because we will simply will not apply any supervision to this output, okay? We will not use this output, but we'll apply this type of cross entropy laws. Cross entropy laws, we have to apply that to train the overall deep architecture for operating for the classification task, okay? So we will only apply cross entropy laws to the final vectors outputted from these classification tokens, okay? So I already told you that there is a classification token here, okay? So, the remaining input tokens are coming from the original input image, okay? But we need extra token, which is called as classification token. And eventually, this classification token will be transformed to the class probability, okay? Are you guys following that? Okay. So we uh, need the number of input tokens for the Vision transformer is number of patches, number of input patches plus one, okay? We need extra classification token, which will be further processed to the class probability, and the cross entropy laws, the only supervision is applied to this probability output, okay? So that is actually the Vision transformer, okay? So they are using the encoder architecture only, okay? And their inputs are becoming the, flattened sub-image patches plus one classification token. And after that, if we get some output, then we will only supervise this classification tokens output to be the class probability by applying the cross-entropy loss. Okay, are you guys following that? Okay, so this is the Vision transformer now we are using. Okay, and yeah, this is the formula for this encoder architecture. So as we see, this is the classification token, and this is the input patches, flattened input patches. I mean, input patches and some I mean, the transformation matrix could be applied. Okay, and this is the embedding, the positional embedding is also added to the low input. Okay, so in this time, the positional encoding in the word sentence, it was the one-dimensional vector, but now it may become the two dimensions. So the positional encoding have to encode two-dimensional space now. Okay, so that's the only difference. And then we will map it to some of the intermediate output by applying multi-head attention mechanism. Okay, and then we will further apply the MLP operation here. Okay, that's the I mean, intermediate process, and we actually repeat this L times, okay? And then at the final layer, we will apply ln last operation to make it into the final output, okay? That's the Vision transformer architecture. Okay, so yeah, this is the simplest form of the transformer that we can use. And actually, 1 year earlier, the DETR, which is the uh, detection transformer, has been proposed by the Meta. Okay, so I mean, this is actually the first paper that applies the transformer to the vision domain, but in the object detection task. Okay, the vision transformer, it is 1 year late, proposed later than the DETR, but I mean, tackles the simpler tasks, which is the image classification. But this DETR is tackling the object detection task, which is a little bit complex compared to the image classification. And what they do is this type of things they are doing. So they first encode the overall images using the pre-trained CNN network. So usually the ResNet architecture is used for this. And then we first extract the image feature. Okay. But I mean, the image features are not normally not, these CNNs are not further trained, but are used for, how to say, extract some image features. And this becomes the input to the transformer architecture. Okay. And DETR, because it is dealing with slightly complex tasks, which is the object detection rather than the image classification, it requires both encoder and decoder. Okay. So DETR is having both encoder, decoder architectures. The Vision transformer, it is only having the encoder, but DETR is having both. Okay. And then it output the set of bounding boxes and the class information. Okay, so we will see this more in detail in the later slide. Okay, so this is more detailed visualization of the pipeline. Okay, so now they are having transformer encoder and transformer decoder. Okay, and also the input to the overall system is the image, two-dimensional image. And using the CNN, we are extracting some features. Okay, and by applying two-dimensional positional encoding, we can make some input to the transformer, their encoders. Okay, so the input to the transformer in Vision transformer was the image patches, flattened raw image patches. But here, the input to the encoder is the CNN encoded image features. Okay, that's the difference. And then by applying the self-attention mechanism similar to the original transformer, they are enhancing the image features. Okay. So the role of encoder in transformer DETR is this is the somehow original image features, but by densely considering each other's responses, the transformer encoder is enhancing the two-dimensional image features. Okay, so here we can obtain enhanced image feature. And then here the cross attention is applied, okay? And I mean, previously in this here, when applying the, for example, sentence translation, here, how to say, have to be the starting token first, okay? And then we have to apply the first French word here and the second French word here to output corresponding. Now here we have to apply some English word, first English word and second English word to output. Sorry, I'm confusing. So here, I mean, by applying starting token, the first French word have to be will be outputted, and in the autoregressive way, we will apply it here, okay? And then the next French word has been outputted. So in the NLP domain, this decoder was sequentially operating. Are you guys remember that, right? But in the image domain, this decoder is not working in the sequential way, but they are operating in the parallel way. That is big difference to the NLP domain. I mean, these object queries are some, how to say, randomly initialized vector. Okay, and during training, these object queries are updated to, I have to say, to minimize overall loss for the training samples. So object queries, I mean, this is some controversial modules in the DETR. So later, many algorithmic improvement has been added to improve the meanings of these object queries. So maybe we will see such variant of DTR later in this lecture. So anyways, these object queries, their meanings are in the initial DTR, we don't have any meaning for these object queries because, but in the NLP domain, this was somehow the autoregressive output, okay, in NLP domain, but in the Vision domain, it is simply the randomly initialized vector, and we will train this random vector during the training to minimize the error, okay? But I mean, the final form of this vector object queries are also having some, also do not have any semantic meaning, okay? That's just the vector that can work, that can make this DTR work, okay? So, but the later, the researchers are realizing that these object queries are one of the reasons why DTR works suboptimal. So later, we will see how we can improve these object queries to have some of the semantic meaning. And also, when we give some semantic meaning to these object queries, the DTR training is becoming faster and it converges better than previous. Okay. Anyways, these object queries are some randomly initialized vector. Okay. And anyways, we cross-attend this randomly initialized vector with the enhanced image feature. which is the output of the transformers encoder, to output each outputs of the decoder. Okay, and also each outputs of decoder are applied to FFN, which is the MLP, and output both class probability and the bounding box information. Okay, so if you set the number of cores as 300, for example, then you will get 300 output from the decoder, and that 300 outputs will be mapped to 300 bounding boxes and class information. Okay, so the number of object queries, how you set these values is actually the number of output, number of predictions you will get, okay, from the transformers. Okay. So if there are more than 300 objects inside the images, you may have to adjust this value to be larger than 300, maybe. Okay, but normally in detail, we set these values as 300. Okay, slightly adjust the values around the 300. Okay, okay, this is the DTR operation. So, until encoder, that is similar to the original transformer, but in object queries are having some meaningless, information in the vision domain. They are just the random vector initialized, okay? But they are, of course, trained and retaining that trained values for the inference, but having no semantic meaning. Anyways, these random vectors are cross-attended with the enhanced image features, and those are independently mapped to some output of the decoder, and they are further applied with MLP to be mapped to the class information and bounding box information. Okay, are you guys following this? And also, this decoder operation is parallelly operated. For each of these object queries, they can be parallelized, okay? But in the NLP domain, this has to be done in the sequential way, okay? When this first output is outputted, and then in the autoregressive way, they input that as the another input to the next output prediction. And somehow they are doing this in the sequential way, but in the DETR, they are not doing such things because there are no sequential meaning in the input domain, okay? Because this is the image domain, okay? Having no sequential meaning. Okay. So this is the the left side, you can see the original transformer, okay? And the right side, you will see the figures drawn in the ECCB 20 paper, okay? Which is the DTR's architecture, okay? And mostly they are similar, but their inputs are now becoming the image features extracted from pre-trained ResNet. And then they will convert it into the kick-query value and applying some 2D spatial positional encoding. And the remaining things are almost same as the encoders of the original transformer. But here you will get the enhanced image features, okay? And here the object queries are the randomly initialized vector. And then you will apply self-attention first, and then apply the cross-attention for mixing these enhanced image features and the object query information. And then you will further map it to with the MLP, and eventually map it into class probability and bounding box information. Okay. Okay, that's the difference in the two transformers in the different domains. And another thing you have to remember for the DTR is, because this is the object detection task, when applying the supervision, when applying the loss function, we may need a few more schemes. So, and another thing you have to remember is the transformer cannot, how to say, distinguish the order of the input. Okay. Similarly, they cannot distinguish the order of the output. Okay. So because of that, we need two stages in the when applying the loss functions. Okay. So, but this is not that difficult. If you understand this properly, then even though the formula seems like complex, but this is very easy mechanism. So for the first thing you have to do is, uh, if you watch this, the set of predictions from the transformer's output, maybe the number of predictions may coincide to number of object queries. Okay. If the number of object queries are 300, then we will predict 300 number of predictions. Okay. But some of them have to be mapped to background, which means no object class. Okay. So, for example, in this type of images, because there are two ground truth objects, if we predict 300 number of predictions, only two have to be close to the ground truth bounding box and their class information, but remaining 298 predictions have to be mapped to no object. Are you guys understanding that? Okay. So, and also the transformer output, we cannot encode any orders. So this is kind of visualizing, how to say, this is, for example, the output from the transformer, but transformer output, they cannot, I mean, describe any orders of their predictions. So we, by ourselves, have to shuffle these orders. So there could be, if there are n object queries, then n factorial permutations there could be. Okay, so if this output from the, how to say, transformer output is, for example, 300 number of predictions we predict, then there could be 300 factorial number of, how to say, permutations. Are you guys understanding this? Okay. So if we, rearrange the orders of the output, then their, how to say, number of making this all possible orders might be 300 factorial. And we have to find among these all combinations, all permutations, which will be called as the sigma n, we have to find the optimal sigma, which is sigma hat, among these all combinations, all permutations. We have to find just one optimal optimal order, and which will be, how to say, best matched with the current ground truth. Okay, so that is happened in the first stage. Okay. So L match, this is somehow the score function that matches these predictions with the ground truth. When matching these predictions with the ground truth, we have to count both of box predicted values and also the class predicted values. Okay, so that's why we are defining some scores for matching the predictions and ground truth. Okay, so what this formula is meaning is among all the permutations, which is these permuted orders, we will find the best matched one order using this score, okay? And that score will be composed of score, classification score, and also the bounding box information. Okay, are you guys understanding that? Okay, so seeing both uh, among these, how to say, 300 predictions, somehow we have to map uh, this prediction is best matched with this ground truth, and this output is best matched with this ground truth. We have to find this type of things first that is happening in this first stage. And for doing that, we are somehow first calculating all the possible permutations, and among these permutations, we will find the one order that best matched with the ground truth. Okay, that's happened in the first time, and there's no gradient update in the first stage. We are just finding the best match, their order, best matched order in the first stage. And second stage, what we will do is for selected order, for this selected order, we will close their bounding box information and classification score to the ground truth. And also we will make this predicted bounding box information and their classification score close to this ground truth. And for all the remaining boxes, we will map it to the background score, background classification score, and also maybe map it to the null for the bounding box information. Okay, so that is actually happened here. Okay, so this is the loss function, and using this, you can train actually the DTR architectures. Okay, their parameters. Okay, so the gradient descent algorithm is actually applied here. But before that, you have to find the best matched order from the transformer's output. And that is actually happened in the first stage. Okay, are you guys following that? Okay. So actually, this is the DETR algorithm. And we already have seen the fast RCNN architecture, which is the extension of the regional CNN algorithm, right? And so, I mean, before this DETR algorithm, I mean, proposed in 2020, the fast RCNN was the state-of-the-art algorithm for the object detection task. But after this DETR, uh, I mean, this is recording the new state of the art. So after this, we are using DTR for the object detection algorithm. Okay. And also after DTR, as I mentioned previously, there are some ambiguity in these object queries. So there have been several improvements. There are several papers for improving the meanings of these object queries in DETR. So we will see that later lectures, okay? And one of the, I mean, these object queries are doing very critical things in the overall DETR architecture. I will only explain that part. So this is the, I have to say, this is the image features outputted from the encoder. So from the CNN image features, we are applying self-attention mechanism to enhance the image features, okay? And here, from the random object queries, we are applying self-attention, and here we are somehow mixing object query information and image feature information to map it to class information and bounding box information. So that's actually how the ETR works. But because these object queries are not having semantic meanings, the researchers, computer vision researchers, uh, have found that the DETR training becomes very slow and sometimes not converged well. So explicitly giving some spatial information to the object queries can accelerate the training of the DETR. Okay, so a later trend of research for improving this DETR was giving some spatial meaning or some semantic meaning to object queries are helping to make this DETR works better. Okay, so we will see that later. Okay, so this is the end of the transformers. Okay, and then we will see some vision language models now. Okay, so now everyone is doing using these visual language models now, maybe at least for language models you may familiar with, like the ChatGPT. Okay, so we will see which type of benefits we can gain when aligning the visual signals and language signals. Okay, so we will see during this course. And before that, maybe we have to see what is the language model. So GPT, which is the generative pre-trained transformers. Okay. So I mean, this GPT is proposed by the OpenAI. Now it is famous for ChatGPT. But in the year of 2018, this GPT-1 has been proposed. And the version of GPT now is 4. Okay. So anyways, but I mean, like almost 10 years ago, GPT-1 appeared. Okay. And they are using this type of transformer architecture as the basic unit. And they are doing some multiple, they are proposed to process multiple tasks in the natural language processing. So wanting to classify some sentence or measuring some similarity between the sentence or doing some multi-choice, solving some multi-choice problem from the sentences. Okay, so their motivation is making some big, huge architectures that is pre-trained for a large data set and wanting to fine-tune those large architecture to apply for the multiple subtasks, okay? And wanting to see they can be generalized, okay? That's the motivation of making this GPT, especially in the language domain. And what they do is first, uh, they are pre-trained the overall architecture using the unlabeled data because when training with labeled data, the label is, I mean, making labels, it also takes lots of labor and sometimes it is hard to get many labels. So, I mean, using labels and doing the supervised learning can limit the number of data sets we can use. So GPT-1, they are, I mean, removing such limitation, wanting to remove such limitation and use the unlabeled data, okay? Unlabeled sentence data, actually. Okay, they are wanting to train big transformer-based architecture using unlabeled data, but by nature, they can exploit this type of, how to say, information inherent in the sentence information, which means, uh, I mean, sentence is composed of multiple words, okay? Which is you want to, maybe you how to say K, maybe, I don't know. If the length of the words is K, then you will have several K number of words, okay? And you can do this type of, you can train the network, not explicitly having the label, but using this type of characteristic inherent in the sentence, you can train the network, which is given the previous word. What this probability means is, given the previous word, you can infer the next word. Okay, so this is not requiring any semantic label, but which I mean, you can automatically somehow naturally obtain this type of information using the sentence. So using this property network, okay? in unlabeled way. So they collect a lot of sentences and then pre-train actually their network to predict the next word given the previous word. Okay. And then in the second stage, what they did was they fine-tuned on the specific task using their ground truth. Okay, so they, after training the big architecture, they fine-tune their big architecture, pre-trained big architecture to the specific task that will provide a small number of ground truths. Okay, and then they watch it that uh, transformer without pre-training their, how to say, average score for multiple tasks. These are some multiple tasks, their accuracy, and average score, that is the average score for these multiple tasks. Okay. If you do not apply the pre-training with unlabeled data, their performance is even less than the LSTM-based approach. Okay. But if we do pre-training and applying the fine-tuning, then their performance is becoming very good. Okay. And also this LM means the task-specific fine-tuning. Okay. Sorry. So even without this task-specific fine-tuning, the transformer that is pre-trained on large corpus data is becoming better than fine-tuned model sometimes. Okay, so we call this type of thing as the zero shot task. So zero shot means we are not given any training data, okay, for some classes. Okay, so given zero training data for classes, but even in the zero shot setting, uh, this transformer, the GPT, is working better than previous uh, fine-tuned, previous supervised models. Okay, and also we see the word of few shot, right? So few shot means we are given several training images for each class. Okay, for example, if we are given one image per class, that is called as one shot task, and two-shot task is meaning we are given two images, two training images for the classes. And because one shot or two shot or even 10 shot, for example, is having few training images. Okay, so we call those things as the few shot task. But if we are given zero training image, then we call that as zero shot, which is we are not seeing any training data for those classes, but even that situation we can becoming better than others. So zero shot is very challenging setting. So this is the term we will see frequently during this lecture. Okay. And the next model, next language model we have to see is the BERT. This is also a language model, but proposed by not by OpenAI. Okay, so this is proposed by third party, and this is also having some uh, transformer-based architecture. I forgot the first names, but bidirectional something transformer. This is the BERT. They are also making some big architecture using the transformer, and then apply very similar technique as the GPT-1. They are applying some self-supervision. How to say, these type of things are normally called as the self-supervision because we do not have to generate some labels, but we can still apply some supervised learning. So we call that as the self-supervised learning. Okay, learning without label data, but still we can apply some supervision using some inherent property of the data. For example, in the sentence, we can predict the next word given the previous word. Those type of things are called as self-supervision. And the method BERT can be applied to other modality as well, but this most of their experiments are done for the text domain. Okay, and what they did, was the two tasks. The first task is the masked language model. The next task is the next sentence prediction. Okay, so masked language model is their own purpose making some blank by removing some word inside the overall sentence. Okay, and then the task is predicting this removed word. Okay, so that's another self-supervised task that we can make. So given the original sentence, we can on purpose removing some word and then train the network to predict this masked word. That's the first task what BERT used to train their network. And the other thing is, given this sentence, actually, they are using two sentences as a basic unit. And if those two sentences are coming from the row sentences, we will call that as the next sentence. So because these two sentences was in the row paragraph, they are coming from the same paragraph. So they are originally in the nearby context. So their labels, we can make their labels as is next, okay? But if these two sentences are coming from different paragraph, okay, coming from totally different paragraph, then their labels could be not next, okay? So this is simple binary classification task. So for this, when inputting these sentences, we can predict not next, but when inputting these two sentences, we can predict is next class. Okay, so this is the next sentence prediction task. Okay, are you guys following this? Okay, so using these two types of self-supervised learning task, BERT trained the huge network. Okay, and then apply it to the they apply fine-tuning techniques to apply it to the specific tasks. Okay. And now this is some comparison to OpenAI GPT-1 and the BERT. Okay, so BERT recorded slightly better performance than the OpenAI GPT. Okay, and even surpasses human performance in some tasks. Okay, but I mean, GPT-1 is having this number of parameters when constituting their basic architectures, but both are composed of the transformer, but their parameters are they are stacking more transformers and having larger transformers maybe. So having only this number of parameters, BERT is having maybe three times larger parameters than the GPT-1. But later, OpenAI buy more GPUs and train larger architectures. So they publicize GPT-2 and GPT-3. And GPT-3, that's also have a lot. They are having a lot of maybe 1,000 times larger parameters than the GPT-1. And of course, they are becoming to have better accuracy compared to the previous ones. Okay. And also, they are publicized in the NeurIPS 2020. Okay, and their titles are like this. So if we scale up the size of the language models, then they can do now starting to work for the few shot tasks. Okay, given if they are given few images, few data for the new class, they can be generalized well and working for those unseen data. Okay. So GPT-3 is having a lot of variant. So from small architectures to this largest architecture, depending on how much they are arranging the transformers, the number of parameters are varied. Okay. And also, but I mean, this is something maybe billion. Uh, this is the smallest architecture, and this is the largest GPT-3 architecture. And the x-axis is denoting the number of examples for the training. Okay, so this is x-axis is the number of training images, and y-axis is denoting the accuracy, the testing accuracy. So when x-axis is 0, that means zero shot task. Okay, so we are given no training images for the task, but measure the testing accuracy. And here, that is the one-shot task that is providing just one training images and measure our testing accuracy. And this is the few-shot tasks. Here is the accuracy for 10, given 10 images as the training data. And we can see when the architecture, their size is becoming larger. So blue lines are the testing accuracy measured for the largest GPT-3 model, and green lines are the accuracy measured for the smallest GPT-3 architecture. And you can see from this graph, uh, I mean, if the parameters are becoming larger, given even with few shot data, the model can be easily generalizable compared to the small models. Okay, so if you have uh, language models which have the largest parameters, then it can be better generalized to few shot tasks. Okay, that's some lessons you can get from this graph. And this is the data set they used to train the GPT-3. Okay, so they are collecting lots of sentences, the text data, okay, and used for training the GPT-3. Actually, there are many, many input data, okay, when training the GPT-3. And yeah, I mean, this is showing their powerful performance. So state of the art, this is the fine-tuned, which is supervised way learned model's performance for diverse data or tasks. But GPT-3, even not seeing any data during the training, which means zero-shot setting, they can be better than previous state of the art for some of the tasks. Okay, even given one shot, one images, okay, they can be very powerful, and few shot tasks, they can be also very powerful. Okay, and GPT-4 even have, larger parameters compared to the GPT-3. And now the recent version of GPT-4 is also having more parameters. And I mean, we can see now, we can experiencing that this ChatGPT, which is the application of GPT, I mean, chatting application is one subtasks, one specific tasks that GPT can do. Okay. So anyways, ChatGPT, when using the ChatGPT, we are experiencing that their generalization power, right? So even we ask some knowledge, which is not maybe seen during the training, the GPT can provide correct answers sometimes, but sometimes wrong, but sometimes giving very good answers, okay? So that's actually what we are experiencing now. Okay? And this is something which was done for the language domain. Okay, but we will now see, which is the very famous work called as CLIP. Okay, so this is publicized in the ICML 21. Okay, and uh, okay, so what they do is they are somehow aligning the image features and the text feature. Okay, so in this figure, there are text, okay? And here there are text encoder, okay? Then we will get several, maybe for the n text input, we will extract some n number of text features, okay? And this is the n images, okay? And we will apply image encoder to extract n number of image features. Okay. And of course, these n number of text descriptions are aligned originally describing these images. So for example, first text description that's describing first image, and second text description that is describing the second image. Okay. Somehow they are coming from the same source. Okay. So we had to uh, I mean, carefully select these image and text pairs. Okay? And then using image encoder and text encoder, extract n number of features for both text and images. And then what we do is we will aligning this image feature and text feature, which means the text encoder's output and image encoder's output, they are having the same dimension. Maybe, for example, D dimension they are having. For example, maybe they are having both these dimensions, maybe. And then if we dot product both, then we can somehow measure their similarity. Okay, and we will maximize these diagonals, which means this is T1, which is the first text feature. And here there are I1, which is the first image feature. And if we apply dot product between them, this is the same, the correct pairs, correct image and text pairs feature similarity, and it should be maximized. But maybe, for example, here you can see, here we are measuring the similarity between second image with the first text description. So all others here have to be minimized, okay? So all other pairs have to be minimized, but only the diagonals, they are describing the correct pairs, image and text pairs. So we are applying the loss functions, which can maximize the diagonals and suppressing all other entries, okay? And by applying this type of loss functions, we can, obtain text encoder and image encoder which is aligned. When text is describing the image content, then text encoder, image encoder, their features will be becoming same now. Okay, that is the important thing that Clip achieved. Okay, and when doing this, actually we can do some zero-shot prediction for the image domain. Okay, so we will see that. So, in the previous ImageNet classification task, what we do for classifying the images are like this. For example, so where we have to train the AlexNet, for example, and the AlexNet's final output should be, their dimension should be the same as the number of classes that we are tackling, right? So the input to the AlexNet was image, and the final output of the AlexNet is this dimensional probability vector, and then we will choose the maximum probability to infer the classes for that image samples. So this is the traditional way of doing the image classification, okay? But what if there is some new class which is unseen during the training, which means somehow both in the training and inference time, in the classical way of doing the, doing the image classification, this final dimension is somehow fixed. Okay, so we always output the probability vector for fixed number of classes. So if there are some new class, then we may have to train this AlexNet, right? Are you guys following that? Are you guys understanding this? Okay. So, it was non-trivial to achieve some zero-shot image classification in how to say, in previous image classification pipeline, which is I mean, for example, CNN and even VIT, we are outputting the fixed dimensional finite probability. So if there's new class comes, we do not have any scheme for extending this for the zero shot tasks. But here, if we align feature and text feature, we can simply achieve the zero shot image classification. I will explain that now. So here, this is the testing images, okay? And we will input it for the image encoder. Then we will get some image feature for that sample. And then we will also encode some text descriptions, okay? Maybe this will correspond to the class label, okay? So we will have the class information in the form of the text, okay? So for that, we feed those class text information to the text encoder, and we'll measure their similarity and find the maximum, find the text that have the maximum similarity as the class for this image, okay? So in this setting, when we can do this image classification in this way, involving both text encoder and image encoder, adding new classes, if their new classes appears, then simply we can add that new class information as new text and extract text feature for that new class and compare it again, additionally compare it. And if that similarity is larger than others, that class could be classified. The image could be classified as that new class, okay? So this is some new way of doing the image classification when we align the image feature and text features. Okay, are you guys understanding this? Okay. So, I mean, this is one benefit of aligning the involving some text signals in the vision domain. So previously, when we only deal with the CNN or transform architecture using only the image signals, zero shot capability is hard to achieve. But when involving the text signals and aligning those text signals with the vision signals, we can easily extend it to the zero shot tasks. Okay, and we will further learn about this clip later. And also, there's some approaches that can extend this clip toward the object detection task. Okay, and also, this is the grounding Dino, which extend the DETR variant. Dino is some updated version of DETR that we learned today. This is the object detector, but we can also align this state-of-the-art object detector, transformer-based object detector with the text, and also see what kind of benefit we can get by aligning the vision models with the text, okay? And we will also see some other tasks, okay? Okay. And most of them are aligning the vision tasks with the text, and we'll getting some benefit. Okay, we will learn about that in the next class. Okay, okay. So let's finish for here for today. Okay, thank you.